raised their hands at level 5 of this maturity model this morning? Who considers themselves an expert? Any level 4 folks in here? Okay. Level 3? Anyone on level 2 or 1? Okay, so this is going to be a somewhat introductory talk. It's going to be technical but introductory. So if you consider yourself a blockchain expert, better move to the other room because this is going to be boring, unless you want to correct my mistakes, which is sort of fun as well. So my goal is to talk about the technical underpinnings of the blockchain. I will talk quite a bit about Bitcoin. So if you're allergic to Bitcoin, another reason for you to leave, I'm going to use that as the means to illustrate how stuff works. I will be talking about proof of work and alternatives to proof of work and about energy and about some of the crypto stuff underneath, although I'm not a cryptographer. So this might be a chance to ask all the questions that have possibly accumulated throughout the day or when you try to make sense of this whole stuff. Okay, so fair warning, don't judge me by the fact that it may be too basic for you. So let's dive right in. First of all, maybe a brief introduction because you folks don't know me. I'm a software architect. I spend my time building software and helping people build software, and blockchain is just one of my interests. Typically, we're involved with building large-scale systems, and blockchain has become a factor in some interesting projects and some interesting proof of work, proof of concept type of things that we've been doing recently. So I faced the task of trying to make sense of this stuff, and the one thing that I'm absolutely allergic to myself is marketecture, which is architecture mixed with marketing. Right, so this is going to be zero marketing. I have nothing to sell, and I hate it if there's something that seems to make sense but somehow doesn't, and then somebody clicks next slide. So if you feel that I'm glossing over stuff or oversimplifying, just raise your hand and ask. It's going to be fine. It's going to be more fun if we make it interactive. So let's dive right in and talk about Bitcoin. So my guess is there is no person on Earth left who doesn't know what Bitcoin is. So this first slide is going to be very, very quick. Bitcoin, everybody knows that Bitcoin is sort of the first mainstream practical application of cryptography to solve a specific problem, not a new problem, but one that's become very interesting about a decade ago, which is to maintain this global history of transactions with guaranteed consistency so that nobody can fool around with it without intermediaries. And this sort of being resistant to fraud and forgery and being consistent over time without having a centralized institution that takes care of that is the key thing about this whole blockchain stuff. It's been created in soap opera style by somebody or some people named Satoshi Nakamoto. We're not going to talk about that. Obviously, it still is the most successful cryptocurrency to date. Personally, I see a lot of Bitcoin hate these days. Which I think is sort of unjustified. We're going to get to some of the criticism as well, but I still think it has a lot to speak for it, which is the fact that it's been there and it's worked for really a long time, and all the crappy things that you heard about people losing all their money and people losing access to their coins and people being defrauded, or all that stuff, all that happened not within the Bitcoin system, but at the edges, at the boundaries of the Bitcoin system with our boring real world. So it's actually always the exchanges and people not taking care of the stuff that led to this thing. So we're going to dive right into a little bit of the somewhat more complicated stuff. Although I don't think it's complicated for you. Possibly we'll see. So we have this cryptography thing, and that's obviously a complicated type of thing. So let's get this out of the way very quickly. We don't need very much to talk about the blockchain and about Bitcoin. It's not going to be too hard. The first thing that has been mentioned quite a few times these days is hashing. So my guess is you know what that is. Otherwise, this is the 10-second explanation. We take some piece of data, we put that into an algorithm, and we get a result. That result is like a fingerprint. This is nothing new. This is something that's been used for checksums and lots of other things, basic data structures like hash tables for ages. And the key thing here is that if even a tiny little bit changes on the left, that stuff on the right changes completely, and in a completely unpredictable way. So if I have a piece of data, I have a really hard time manipulating it so that I get a specific hash result, right? That's the feature, that's the core function of a hashing algorithm. Another key point is that it's irreversible. You can't go back from manipulating it So essentially, if I pose you with a problem like make me a particular hash, And giving you the opportunity to change the data gives you a very, very tough challenge. Right? So if I present you with this piece of data here and say, well, please generate a hash key for me that starts with a number of zeros, let's say 4 zeros. That's going to be a tough thing. Do you have any strategy how to do that? Anybody got an idea? What would you do to solve that problem? Anybody? Keep trying. Right. So the technical term is brute force. Right? So we keep doing the same thing over and over again. We have to run the hashing algorithm again. And then we check the result. That's something that we can do very quickly. We can very quickly check whether this result starts with 4 zeros. If it does, yay, we've solved the riddle. If it doesn't, we have to try again. And there is no way to get around that. There's nothing you can do. There's no heuristic. There's nothing that'll speed this up. The only thing you can do is keep trying and keep computing and keep burning energy and investing, or depending on how much you like this idea, investing or wasting energy to produce this particular result. Okay, so that's the first building block we need here, hashing. Everybody with me still? Hopefully. Okay, so first thing. The second thing is the relationship between public and private keys and the whole idea of asymmetric encryption. So this is something that you've all been using if you have ever exchanged an encrypted email using PGP or S-MIME, or in fact if you have ever used HTTPS, because even though while you're exchanging data with that other party on the other side, things are done in a symmetric fashion. The original key is exchanged using asymmetric cryptography, which essentially works like this. You have a randomly generated private key. Randomly means that this got to be some real randomness in it, like maybe you moving your mouse around or some system sampling white noise from the atmosphere. I don't know, something that gives you real randomness. And then, or you throwing the dice for 256 times. Once you have that private key, you can derive what's called a public key from it. And this thing, this key pair, as it's called, has some very interesting properties. For example, you can use it and use the private key to sign a piece of data to derive or to arrive at a signature, which then anybody who has access to the public key can check. Right? So that's the basic relationship here. If I have a private key and only I have access to that private key, then I'm the only person who can produce a value that, when checked with the public key, which was derived from my private key, will produce true as the answer. Yes, this checks out. So if I ever give somebody else my private key, they can do the same thing. This is what protects me from everybody else. This is why it's very important to keep your private key private. This is why it's so hard to explain this to normal people. We're not geeks, right? So we have this relationship here. We also have the relationship of being able to encrypt something. So if you have my public key, you can use it to send me a message that you have encrypted with my public key, which means that only I, again with the access to my private key, can decrypt again. But that's not as important here as the signature part. Is everybody still with me on that as well? Okay. So those are all the basic cryptography building blocks that we need to understand the rest of the stuff. So the rest of the stuff starts out with a little bit of the vocabulary around Bitcoin, right? So we're going to go very briefly over this universe of things. Again, I'm using Bitcoin as the example, and I will be talking about others, and I will try to differentiate Bitcoin versus other public approaches as well as private and permissioned approaches, right? So that's going to be later on. But let's start here. Bitcoin itself, we talked about it, is sort of the thing, right? The first practical application, the thing that invented the blockchain. Of course, Bitcoin didn't invent the blockchain, but Satoshi invented Bitcoin as part of Bitcoin. The blockchain concept was introduced in this particular paper. So it's the technology, it's also the name of the currency, and you've probably heard that Bitcoins are created via mining. We'll talk about that quite a bit. And we have subunits, so you can split a Bitcoin in smaller units. There used to be a mistake. I don't know, is this correct? I think it's correct. Whatever, it doesn't really matter. This is the smallest part, the smallest unit that you can spend on the Bitcoin network. And actually the ledger or the blockchain or the whole system, so to speak, doesn't maintain balances in accounts. It actually only maintains transactions. So coins are never maintained as a balance on some bank account like structure. It's the sum, it's the aggregation, it's the in functional terminology would be the reduction of all the transactions that ever happened that'll yield a certain value of coins for particular addresses or people involved in the whole thing. So that's the It's the overall picture. Now, to do something with that, to do something with the Bitcoin network, you require nothing but the skill to write a program, right? So you could do that. If you're a programmer, then you could spend something between a day and a week writing what's called a wallet, right? So the wallet here is the piece of software that connects you to a blockchain, in this particular case, to the Bitcoin blockchain. The wallet is a piece of software that does not hold your coin, even though it sounds like it would. It actually maintains your keys, so it's more like a key store. The wallet is also what's typically used to generate the keys. So you use the wallet software, you click some buttons, you enter some randomness, and then maybe it produces a number of private keys, public keys, and addresses. I didn't mention them. Addresses are one more step derived from a public key. It doesn't really matter for the rest of the discussion. You could simplify a tiny little bit and say that those keys are used to sign transactions. So the wallet sends a transaction to the system. And for this transaction to be valid, it has to be signed. And that signature is created using the private key that you've created in your wallet. So while you could write that software yourself to take part in the Bitcoin network, you typically don't. Typically, you reuse an existing implementation, of course, which exists for basically any platform, whether it's your PC or a Mac or typically some mobile device, or whether it exists online, which is typically a very bad idea because you don't want to give anybody else your private key. If it's an online system and you give it your private key, then you've violated the first rule of private keys, which is don't give them to anybody who's not you, right? So don't do that. Don't use an online wallet. Most people I know, it could be interesting to ask this around. So most people I know use their phones for day-to-day interactions or for not that amounts that are not that big, and switch to something else like a hardware wallet for larger amounts, because you're sort of trust them a little bit more. A hardware wallet is essentially a little piece of hardware that has firmware embedded that operates the actual wallet, right? So there's a way to interact with it. The added security is comparable to the added security you have with the little devices that you use when you do credit card payments, or the fact that even if you're maybe buying a ticket at the railway station, you're interacting with a big machine to actually select the ticket, but then when you actually type in the little PIN number, it's with a little device that's the specific device that maintains integrity because it is completely closed to the outside world and does computation offline that wallet. Okay, so the wallet is the key store. It creates the keys. You can create as many as you want. You specifically can create as many addresses as you want, which addresses anonymity a little bit, but not too much. But essentially, the wallet maintains the keys and allows you to send transactions, which is the next concept that we have here, right? So in computer terms, in computer science terms or programming terms, a transaction is a data structure, right? It's a data structure with a specific layout. That layout is defined by the C++ implementation of the original Bitcoin software. It has a number of fields laid out in a particular with a particular offset. As long as you're able to produce that data structure, you can send that data structure to the Bitcoin network, which is a peer-to-peer network, and we'll talk about that later. Now, within Bitcoin, as one specific example of a blockchain, the application that's managed by this blockchain is the currency part, right? It's the transaction part. So the transactions allow you to perform financial spending, right? So to do that, you have inputs and outputs. It's a little bit like a cash transaction. If I go to a store and they ask me to pay 12 euros, then it's pretty likely that I don't have exactly 12 euros in my pocket. I might have something like a 10 and a 5 bill, so I give them 15. I give them 2 bills, and they give me back 1 euro and 2 euros, so I get back 2 outputs, and the third one, the 12 euros, go to the merchant, right? That's sort of the analogy here. Inputs and outputs spent during a transaction. Now, the obviously necessary thing here is that I can only spend what I own. So I can only use inputs that were outputs to me in previous transactions. Make sense? So that's essentially the model here. Multiple also mentioned that. There is sort of a thing that's puzzling at first, which is when you look at a transaction, there are tools that you can use to look at the actual transactions of the Bitcoin network. You'll see that there's an amount less. So somebody wants to spend 15 euros or 15 millibitcoin or whatever, and they use unspent input with a worth of 16, but they only get half as a return, which means there is 0.5 going somewhere, and that actually is a transaction fee that will go to the miner. We'll get to that later on. Sole signature kind of thing is a little bit simplified. Actually, we talk about encumbering the outputs, which is a little bit too much to explain right now. Let me just gloss over this, so I'll get back to that a little later on. This essentially ensures that only the recipient of the money can spend the money, right? And the transaction will be sent to any node. The node is a technical term for any participant in the peer-to-peer network, and then the node will propagate it to other nodes within the system. Am I still achieving all of you, reaching all of you? Okay, please. You can also tell me to speed up by looking very bored. Okay, so I'll try. Yes, please. Sorry? Right. So who's running the nodes? So essentially, anybody who's running the particular piece of software runs a node, and they are typically running on whatever sort of a Linux system you have available. I believe the majority will run on Linux. Some of them will run in the cloud, although it's pretty expensive. Some of them will run on standard hardware. Most of them will run on specific hardware built for running nothing else. But we'll get to that a little later on. If you want to run a node, you can do that. You can download the software. You can fire up the software. It will start running. And the first thing it'll do is it'll download the blockchain. We'll get to that in a second. But as soon as you have the full blockchain, you have a fully operating full node that'll then be part of the Bitcoin network. And you can decide whether or not you want to do mining or not. If you don't want to mine, then you just are being a good citizen of the Bitcoin network and offering to help everybody else exchange value on the network. Right? Yes, please. Not really. So the question was, is there any benefit to having a non-mining node? Yeah, to the network, but not to you personally, because you're not incentivized. Nobody's paying you for running a Bitcoin node. The only way to make money of Bitcoin is to do something illegal or to do mining. And mining is far more lucrative, which is an important aspect of the whole system. Okay? Good. So when we have those transactions, the transactions in themselves are validated, right? They're checked. Anybody can do that. If you write a piece of software that operates as a node, this is one of your tasks. You have to validate a transaction. You take a look at a transaction and check whether it's okay or not. But transactions are also included in a larger structure, which is called the block. And a block is essentially a list of transactions, right? So in data structure terms, again, a block data structure has links, if you want to call them that, references, pointers, actually hash values of transactions. Let's say a block references 1,000 or 2,000 transactions that have occurred. And the blocks themselves are validated as well. Anybody can check whether a block is valid or not. A block is valid if all the transactions in it are valid and if it includes a valid proof of work. That's sort of the most important thing to understand about the whole concept, which is why we'll be talking a little bit more about that in a second. A block also references the previous block. So every block has a reference to 1,000 transactions or a few hundred, whatever, and a pointer to the previous block and this proof of work thing. This means that all of the blocks form a linked list, also called a chain, which is why the whole thing is called a blockchain, right? Because it has this list of blocks that reference each other. Actually, blocks. Yeah. So when you go back to the very beginning, there's what's called the Genesis block. This is the only block that doesn't have a predecessor. It's the one that's been created by Satoshi when he published the software, right? It's embedded. So if you write a program or if you write a full node software, then one of your tasks is to use the Genesis block and then validate that all the blocks form a valid chain from this starting block up to the whatever 450 or 480,000 blocks that we have today, and each of them can be validated. And that's essentially what a full node does. It downloads all of the blocks, including all of the transactions that ever happened. So that'll take you something like, I don't know, depending on your network speed, maybe a day or two, because it's now 180 gigs or whatever. You have to download that stuff and validate all that stuff, and then that's what you operate when you run a full node. It's a little different when you run a piece of Bitcoin software on a phone, right? Because you wouldn't want to download 164 gigabytes of data. So what they do is they do a lightweight variant of the whole thing. They download only the headers of the blocks, and then they download the blocks that you're interested in because they include transactions that you have inputs or outputs related to. Right? So it's only a small subset of all of the data that's downloaded if you have something like a phone that runs your software here. I'm going to explain, and that's the most important thing here, why the number of blocks relates to the level of trust. I'm going to justify, or try to justify, why we do all this stuff, right? So, important question between, everybody still with me here? You're fine? Okay, so we're going to dive into this proof of work thing. I mentioned the thing about this riddle. Do you remember the hashing discussion at the beginning? This is essentially what's being done on the Bitcoin network. And on any blockchain that uses the proof of work mechanism to ensure validity of blocks. The goal here is to find a hash value that matches a particular difficulty target. That difficulty target is, slightly simplified, the number of zeros. Let's say my goal is to find a hash that starts with 1 0. That's a lot easier than finding a hash that starts with 10 zeros. Because there are a lot more that start with 1 0 than there are that start with 10 zeros. So it's going to take me a lot longer if the difficulty target is higher. Make sense? So this is essentially what happens during the calculation of the proof of work. If I run a node, I can decide to run a node that is a mining node. If I run a mining node, one of my tasks is, or one of my goals is to find new blocks. So this is what happens. The transactions get sent to the nodes from the wallets. The transactions get propagated through the network, so all of the nodes in all of the Bitcoin network have their own little copy of all the pending transactions. And then the mining nodes try to find a block. To find the block, they grab a bunch of transactions, they construct a new block, they point to the previous block, the last block in the chain, and now they have an almost complete block. It's almost done. The one thing that's missing is the proof of work. So what they do is they have a field that they can use to put in any value they like, and they start playing around with this value and calculating and calculating and calculating again until they get a block that validates, that meets the difficulty target, where the hash value of all the content meets the difficulty target that's been set out. Did that make sense? If so, you've just gotten the concept. If not, ask. So the only way to get a valid block is to keep trying to change the value of that nonce. And once I have found a block as a miner, I'm really happy, because one of the transactions that I'm allowed to include in the block is one that gives me 12.5 Bitcoin. That is something like, I don't know, 60,000 euros as of today, which is a pretty significant, well, who knows, maybe it's 59,000 or 58,000, who knows. That is the reward that I as a miner am aiming for. I want to find a block so that I can get the mining reward, this 12.5 Bitcoin. I also get the transaction fees, so the leftovers from all the transactions that I've included, so I likely pick the transactions that are most valuable to me. That's all Bitcoin specific, the transactions and the value and the reward thing. The blockchain structure, the chaining of the blocks, and the fact that it's this proof of work thing is done in multiple blockchains, not only in Bitcoin. Now, what happens when I've done that? I, as a mining node, am just one of the many nodes that do that, right? So all over the world, mining nodes try to find a block. Once they've found a block, they publish it to the network. Hooray, I've got a new block. Please use this from now on. Just a second. Now the block, again, travels across the network, in the peer-to-peer network. People get this block, and if I'm a miner, then I now get a block from somebody else, and I take a look at that block, and now I have to make a decision. Do I continue trying to find a new value? Maybe because I think, well, probably not everybody has this block yet, so I'll just hope that I'll find my own block within the next millisecond, and then I can send mine instead of this one. Or do I consider this a lost cause and say, okay, I throw away this thing, make this one the new preceding block, and start calculating again? And that is typically what nodes do. Yes, please. Mm-hmm. Yes. So the transactions fees are currently the negligible part. They're not what makes miners rich. The more important part is this Coinbase transaction, the transaction that actually creates new Bitcoin. It's the only way new Bitcoin can get into the system. The amount of Bitcoin is limited, like I think it's 21 million Bitcoin. It's the ceiling, the maximum value. So the reward has been continuously reduced. It used to be 50 Bitcoin at the beginning. They went to 25. Now it's at 12.5. It'll halve again in a year or so, I think. It'll be at 6 whatever. So it halves, and then it goes to 0, whereas the transaction fees become more and more important. Okay? Any other questions so far? Yes, please. Mm-hmm. Mm-hmm. Yeah. So the question is, why do you keep trying? Don't you always get the same number if you hash the same thing? Yes. That's why there is one field that you're allowed to set to a random value. So there's all the data of all the transactions, the preceding blocks, lots of reference and metadata and headers and stuff. And then there's one field that you can set to whatever value you like. So you keep varying that value, and then you calculate again, get a different hash value, vary again, calculate again. Does that make sense? Yes, I don't know how long it is. It's a random multi-byte value that you set to whatever you like. Oh, yes. Yes. But it's completely your decision which transactions you pick. You could decide to pick just 5. That would be not very nice of you, but if that's what you want to do, you don't get as much money as if you included 1,000, because you get the transactions fees as well. But it's definitely the case that different miners will pick different transactions. They won't all have the same transaction pool, because some transactions will still be in transit. They will already have arrived at one, but not at the other. And they will all follow different strategies, right? Do I take more with more transactions? Probably not. I'll always pick transactions with the highest transaction fees, and then I'll have some heuristic on how to create my block, because there is some relation between the size of the block and the time it'll take me to do the hashing. Not a very big one, but there is a slight one. So I'll have to find a good balance between the different goals that I have. Not interesting enough. Yes. So yes, excellent point. So what happens if the network becomes congested, right? If you have more transactions than the system can handle, how long can it take? It can take an awful long time, as people found out last December, right? When Bitcoin was at its all-time high, like $20,000, something like that. People were trying to buy and sell Bitcoin like crazy, but the system couldn't handle it. Because if you think, what will happen here is the difficulty target is adjusted so that it'll take about 10 minutes to find a new block. If you do the calculation, 10 minutes, that's 600 seconds. If you then calculate, let's say, 2,400 transactions per block, it's very easy to arrive at 4 transactions per second, which is a pretty sad statistic. Right? That's not a truly global scale in anyone's imagination. So there have to be ways to get it up. It's a little better now. Because there is more, but it doesn't. I can't get into too many details here. But essentially, the network can become congested. You can wait an awfully long time. At the moment, that's not a problem. It used to be a problem for like 9.5 years. There was really this one phase last year where it really, really sucked to own Bitcoin and not be able to sell them. So still, you're competing with others. There's no guarantee that your transaction will be processed, and you have no way to take it back once you've put it on the network. It's there. You can decide to put a new one in there. You won't be able to spend the same money twice. That can happen for other reasons, for very important reasons. But essentially, you're at the mercy of the miners, including your transaction in their blocks. Everybody still with me? Yes, please. Excellent question. So if you have the condition where 2 miners found a block at roughly the same time, or even more than that, what do you do? So essentially, the chain is more like a tree, because it forks, indeed. But it's a tree where the thinner branches are very quickly cut off again. Right? So it branches for a short amount of time, but it very quickly converges again to the strongest branch. This can take some time. So if you want to make sure that your transaction has happened, it's not enough to see that it's been included in a block, because that block might be on a branch that will be cut off. But if you wait a while, typically about an hour, you have 5 following, or 6 blocks, right? 6 blocks. The 6th to last block is the one including a transaction. You can be reasonably, absolutely sure that nothing's going to happen. I'm going to explain why very shortly. And that sounds bad. Like an hour doesn't sound great, right? But an hour is fantastic because you don't have to compare it to the amount it takes to process a credit card transaction. You have to compare it to the amount of time you have to take back that credit card transaction. If I pay something, then I can 3 days later call American Express and say, come on, this was not me. And then the merchant and I will be discussing whether or not I really paid for that. That can't happen with Bitcoin. If you pay for a Ferrari in Bitcoin, after an hour, the Ferrari dealer is perfectly fine in giving you that car. Right? That's sort of okay, right? Even for an e-commerce scenario, before you send out the $10,000 TV, waiting an hour is not a problem. If I buy a coffee, then I can risk it that I can risk that something goes wrong. It doesn't really matter, so I won't wait that long. That's the theory, at least. Yeah. So the miner who mined the branch doesn't get a reward. Yes. So essentially, because not only that, not only the miner who found a block and was on the branch doesn't get a reward, no miner gets a reward except the one miner who got the successful block. So if we've got a few thousand people wasting CPU cycles on calculating this stuff, and none of them will be rewarded except the one who got the block. Right? Yes, please. The reward they'll get is the transaction fee. So then they will not get this Coinbase, this mining reward, this newly minted Bitcoin, but they will still get the reward from all the transactions included. So that will probably have to go up a bit. Well, the market will tell us, right? They won't mine if it's not enough. Miners are very selfish people. So that is one of the cool things about the truly innovative things about Bitcoin, and one thing that got it to take off. It's a mixture of cryptography, a little bit computer science, basic programming skills, game theory, economics, applied security. It mixes all of those things in a very successful way. And I need to explain that because it's sort of the one thing that is the justification for the proof of work thing. So proof of work is this concept of solving the riddle, right? Which we've now all grasped. The problem here is that, or the reason it's being done that way is because it's hard. That's why it's been done that way. Because it's hard to create a valid block, it's very, very expensive to forge a block. To forge a block is as expensive as finding a valid block. Right? Except if you find a valid block, you get the 12.5 Bitcoin reward. So whatever you do with the forging better give you more money than the 12.5 Bitcoin. Now, if you wanted to change history, that's the only thing you can do, right? So if you wanted to, say, buy a house with your Bitcoin, and then use the same money you just spent on the house to also buy a car, it's the double spend problem. Then what you would have to do is somehow make that transaction undone. Right? It's already happened. It's already recorded in the blockchain. It's part of a preceding block. You can't take it away because then the stuff would be valid. Right? Every node would reject that. So what you would have to do is start at the block where your transaction is included and then calculate new forged blocks. But the rest of the world is already 10 steps ahead. So you would have to be faster than the rest of the world in creating one block when you try to create 10 blocks, which makes it a completely idiotic problem to solve. If you have that much computing power, it's much more useful to use it to mine Bitcoin, which is, again, part of this game theory economic motivation kind of thing. Right? It's more useful to use the hash power you have to do Bitcoin mining as opposed to trying to fool around with that stuff. You can't spend other people's money because you don't have their private keys. The only thing you can really reasonably do is try to spend your own money twice, and that's not a very lucrative a strategy for defrauding people of their money, right? Yes, please. Mm-hmm. Yes. So what typically happens is that a block includes something like 1,000 to 2,000 transactions. Don't shoot me if that's not exactly right, but that's around roughly the number of transactions per block. Does that answer your question? Mm-hmm. Mm-hmm. Yes, 60,000 euros. Yes, that sounds really expensive, right? Doesn't it? Yes. No. You're not. First of all, you're getting Bitcoin. You're not being paid by the people who did the transactions, right? That's not what happens, right? So you're getting paid in the currency of the system itself, which is an important thing because the value of that is related to the value the currency has in relation to the outside world. But it's a good question because it's at the heart of what people question about the validity of the whole concept. Well, why does any of this make sense, right? Why isn't this completely stupid? And the reason is that for this investment, for this wasting of all this energy, for this thing, you get trust in the whole system. You know, I'm 100% sure if I do a Bitcoin transaction and it's included in a block that's 10 blocks down the line, then I'm absolutely sure this is not going to be forged. I don't have to trust a central bank. I don't have to trust any intermediary. I don't have to do any of that. So the amount of money given to the miners, which translates into the amount of energy and hardware and other costs that they have to spend, right? This is, of course, a market function. The amount of effort and money that they spend is related to the trust that they create by maintaining the system. Is it worth it or not? I don't know. You tell me. I mean, if you asked me, then I would say if we shut it down today, you know, if Bitcoin disappeared today, then I would say it wasn't worth it. It hasn't yet created anything beyond speculation and, you know, made crazy people rich. It hasn't done anything good for society. But I think it has the potential to do that. So we will see in 10 years from now whether maybe this is the most successful experiment ever done in computer science. I absolutely don't know. Right? But if you don't believe in this investment, then of course it's complete craziness that you waste that much time. Well, yes and no, because at the moment I don't know whether anybody knows the current transaction fees, the current average transaction fees on Bitcoin today. Sorry? 80 cents. So at the moment you wouldn't do that. At the moment to pay me €1 in Bitcoins, you would have a transaction fee of 80 cents. So that's not reasonable, right? So 80 cents, you'd probably use it if you give me €100. Right, so the market sort of regulates it. Back when the transaction fee was like a 0.1 cents or 0.01 cents, then it was perfectly reasonable to pay for 2 cents with a Bitcoin transaction, because the miners only got a very limited amount of money, and of course they didn't invest the same kind of stuff. You could mine Bitcoin on your laptop. 8 years ago, I have friends who did that. Some of them lost their USB drives and let's not talk about that. But you could use your laptop to mine Bitcoin. And the value of Bitcoin relates very strongly to the amount of money people are willing to invest in Bitcoin mining, which relates to the reward that they need, or the other way around, however you want to phrase it. But you're right, at the moment it's expensive. Yes, absolutely. And you could also argue that's because it only does 1,000 or 2,000 transactions per block, right? If it did 100,000 or 500,000 transactions per block, then that would be awesome, right? The problem here is that if it did, the economics would change again, because having blocks with 500,000 transactions makes it a much tougher problem to do the hashing. It's a much larger data structure. It takes you much more time, you need much more memory to do the same stuff. So this will lead to more centralization, because fewer people will be able to afford the mining hardware to do that. The moment you can spend like, I don't know, 10K and you have a very decent mining rig that you can use to make money. If blocks were 10 times the size, maybe you would have to spend 5 or 20 times the money. I don't know the exact relation here. Everybody still with me? Okay, so a warning. I love doing the Q&A thing, but we're not going to get through my slides. If this is fine with you? Okay. Yes, please. Excellent. How is the difficulty target set? So there's to be quite honest, I'm not 100% sure. So I'm giving you a sort of weasel answer, and some of you can add to that if you want to. So essentially, there are some things that are hard-coded into the software, right? So the software will, I think this is the case with the difficulty target, it will, at some points in time, no, It's the case with the mining reward. So the halving of the mining reward is related to the number of blocks. So every, I don't know, 200,000 blocks or something like that, the mining reward will be cut in half. Other things like the difficulty target will be adjusted dynamically based on sort of what the majority do, right? So if the majority reckon that it's going to take longer than the envisioned 10 minutes, then they're going to reduce it. If it takes less than the 10 minutes, then they're going to adjust it. And if the majority of the software nodes participating has reached a consensus, that's sort of governance consensus, right? That this is to be changed, then it gets changed. Yes, please, Dino. Excellent. Good. So it's a fixed time, but it's based on the average over the excellent. Thank you. Okay. Ready to move on? Okay. So now I've said a lot of stuff, so I'm going to switch over a little bit of that. So I briefly mentioned this when I talked about laptops, right? And so you were able to do the mining on laptops. It became interesting to do it on other hardware like GPUs, and then you can sort of create this continuum of possible hardware choices here, where you go from a very general purpose CPU over a graphics unit, over a field programmable array to some sort of special purpose built hardware. And that's what most people do these days, right? So if you do Bitcoin mining, this is done using the most advanced hardware that is in existence today, because it's worth so much money to do that. So those chips are created just for Bitcoin mining. And there are numbers of ways. So what I've explained now, this very simple hashing thing, is actually SHA-256 twice. But there are other alternatives. So other blockchains that use proof of work use other algorithms. Not the simple hashing thing, but they do something else. And there's also special hardware to do that for the different variations. I mentioned that because I need it as a prerequisite for the energy discussion, which we've had to a certain part as well. So one of the things, I think Ingo did this in his keynote this morning, one of the things that happens a lot these days is that people dismiss proof of work because it's such an attack on our planet, right? Others defend it. So I've made my life easy and included both positions for you to choose from, right? So position one is, this is a catastrophe, right? We shouldn't be doing this. We really shouldn't. Because we have a continuously increasing demand for the whole thing. If you compare the energy consumption of Bitcoin to, say, the Netherlands, right? The Netherlands is at 106 terawatt hours per year, whereas Bitcoin is at 65. Is that a reasonable relation? Is Bitcoin worth spending so much energy on? And if you take this position, this is completely crazy. It's like, nobody in their right mind could do that. In fact, if you talk to certain people, they will really personally start to hate you if you have anything to do with Bitcoin, because you're destroying the planet. Little to no value, only speculation. Of course, because it's so energy intensive, it'll use the cheapest and dirtiest energy sources that are available. So it'll be done in countries where nobody cares about the environment, and use the dirtiest coal. And then you will, I'm talking about the US, obviously. So you'll do the dirtiest coal to do that. And then you also have this completely useless hardware, right? Because you create ASICs for a specific variant of the algorithm, and then the blockchain authors or the people who maintain it will try to circumvent your ASIC, because ASICs are not something that decentralize a blockchain, right? They do the opposite, because they create a higher barrier to entry. So people want to have ASIC-resistant algorithms, and so, which means the hardware that people just bought becomes completely useless, because you can't do anything other with it than mining a previous version of whatever blockchain they were built for. And I think those are very good arguments. So I think proof of work has a problem. Everybody who says this is not a problem at all, I find that kind of weird. On the other hand, you could argue this is really no big deal, because we're viewing it from the completely wrong angle. Essentially, the first thing is the demand will, of course, not increase linearly, right? So we have a sort of curve like this, so it'll stay at about this. There's no reason to expect that the energy consumption will be 3 times as high a year from now, because then you can't extrapolate from that. It is more useful than Christmas lights, which consume more energy. Okay. Maybe one of the problems is that costs are transparent, right? You can see how much or you can calculate how much it costs, whereas all of the bank buildings that are lit at night, all of the people using their cars to drive there, all the computers running in the banks, data centers, all of the financial system. If we got rid of all of that, would that be a net benefit or not? I don't know. We have no idea how much energy the finance industry consumes, and we have no idea how disruptive this whole thing in general could be. We could also argue that we don't need multiple proof-of-work chains. Maybe it's just one that's going to emerge, and maybe the world can afford one proof-of-work chain. Right? That could be a reasonable thing. You could also argue that it's not at all the dirty energy. It's the clean excess energy that's being used. Right? It's maybe in Iceland or another place where some sort of power station produces power that nobody can take from them. Maybe you could use it and convert it into Bitcoin. Bitcoin becomes sort of the conservation strategy for energy that would go unused otherwise. Whatever. Right? So you can decide to view things this way as well. Now, again, I'm undecided on the whole thing. What I do think is that, as of now, there is nothing, absolutely nothing, that can compete with the proof-of-work algorithm in terms of maturity and reliability. There is nothing. There are lots of alternatives. I have a whole slide deck, which I won't go through right now, about alternatives to the proof-of-work algorithm, like proof-of-service, proof-of-authority, lots of other variants that you could do there. But none of them is deployed on the scale that proof-of-work is. None of them powers something like Bitcoin. And most people who tell you they have found excellent alternatives to proof-of-work either don't know what they're talking about or they're lying at you in your face. So be careful of that. Okay, so we've got 50 minutes left, which is kind of okay because I said most of this. Yeah, we went to most of this. So one thing that I want to mention as sort of the second step here is this little known thing called Bitcoin script, because I simplify it a bit. Bitcoin, in fact, has always had a capability that few people know of, which is the fact that it includes a scripting language. So Bitcoin has this very, very limited scripting thing that essentially is used with every transaction. So signing a transaction is a little different than what I made it sound like. Essentially, using your private key, you provide a value to a little script that's stored in the transaction, and only you can provide the value that will make the script return true, so that the predicate return true, so that the transaction can proceed. That sounded weird. Ignore it. The key idea here is that the scripting capability in Bitcoin allows for very simple things, like, for example, multi-signatures. You could decide that only if multiple people sign off this transaction, they can spend this money because it's owned by multiple people, right? Yeah, I'm not going over that. The key thing here is this first bullet, intentionally limited. So the Bitcoin people decided not to include a full-featured programming language, because including a full-featured programming language is sort of a security risk. And they decided maybe we don't want that, and went with a very, very simple thing. If any of you are real programmers and know something like Forth, it's a little stack-based machine, not Turing complete, no jumps, no loops, right? Very, very simple, no halting problems. So that was their decision. But it's kind of cool to be able to script a blockchain, which brings us to Ethereum. And that's going to be an Ethereum talk later on. But essentially, the idea was available in Bitcoin already, and it spread to Ethereum as the next big platform here, which is in many regards very similar to Bitcoin, right? So it's typically public, although there are private versions as well, has its own currency, has those blocks, a little faster, uses proof of work, but will switch to proof of stake once they get it working. The key difference here is that it's a platform for arbitrary contracts. So you can program Ethereum. Whereas in Bitcoin, the only program running on Bitcoin is transactions. Ethereum can run any program. And there's one program that's already deployed on Ethereum, which is the currency protocol for Ether. But in fact, you've probably seen that there are multiple currencies on Ethereum now, because they have sort of standardized the contracts for that. And this whole contract, a contract is just a program or a script, right? A smart contract is a dumb script. That's all it is. There's nothing fancy about it. It's just a script running on the blockchain. And it can maintain state, and the state is maintained on the blockchain as well. So Ethereum is different from Bitcoin in that it has two kinds of contracts, or two kinds of accounts. It has this externally owned account, which is very similar to a Bitcoin address, right? It's something that you can send money to, transfer money to. But it also has this concept of accounts that are contract accounts. And those accounts are not externally owned by a human being who makes decisions on what to do with their money. A contract account is a program where you can read and look up what it does with the money. And it can not only receive money, you can actually have arbitrary methods on a contract. If you are OO programmers, a contract on Ethereum is essentially an interface with a number of methods. And you can interact with the contract by calling its methods. You would say it's a class because it also has state, right? It has instance variables. And it can, in its implementation, it can change its instance variables as the result of a method being invoked, and it can also invoke other contracts. That's essentially what Ethereum does, which is freaking cool. Right? That's a very nice idea. And one of the reasons the contract metaphor is so interesting is that this is essentially what we're interacting with all the time. If you have some financial relationship, some business relationship to some entity, to some company, then essentially you've agreed to a contract, right? Maybe you've just clicked through on their website, or maybe you really have a written contract that has been signed by both parties. But this contract says what will happen. You will pay them 10 euros every month, and they will stream TV series to you, or whatever, right? That's the contract. Now, turning that into a program is a very interesting thing. Now, that security thing might be, you might wonder about that, because if I'm allowed to run my code on somebody else's platform, who stops me from running bad code on there? Who stops me from giving them a never-ending loop or something, right? A looping program that will slow down their platform forever. The concept here is gas, which is a very cool invention by the Ethereum people. That's essentially the idea that you, as the caller of a method, have to provide the fuel to execute the method. So the fuel is provided in the form of gas, which is actually money, right? So you determine the amount, and the execution of the actual method will, you could say, with each CPU tick, it'll reduce the amount of fuel, and once the fuel runs out, the method stops and returns the result, and the money is gone. Does that make sense? That's also a very cool idea, I think. Very fascinating stuff here. Ethereum is pretty cool because you can program in a number of languages. I'm not going to go over all of that. Most important thing here is Solidity. So if you want to play around with that stuff, Solidity is a JavaScript-like typed programming language that runs on top of Ethereum. Actually, they're at the moment considering moving it or embedding WebAssembly, which makes it sort of interesting as a general purpose platform for any programming language that can target that VM environment or that environment. Essentially now, instead of validating a block by checking whether the transactions conform to the Bitcoin protocol, on Ethereum you have to actually run the program, because behavior is specified from the outside. So if I want to publish something on Ethereum, if I publish a program on Ethereum, what I do is I use a transaction to send the code to the Ethereum platform, and then that becomes part of a new contract account, right? There's a new thing now on Ethereum. It sits there and it waits for someone to interact with it, right? So that is the concept here. That was a very, very quick Ethereum introduction. Are you fine with that, or you want to ask something on that? Yes, please. Yes. Mm-hmm. Yes, so the question is about the traceability and anonymity of transactions within one of those public blockchains. And there is essentially none. So essentially it's not anonymous. It's pseudonymous, so you don't have clear names, you have addresses, and you can create a new address for every transaction if you want to. Your wallet, if it's a new modern wallet, will support that. So you could say that every time you receive money, you show people a new address. They will always pay to a different address, and nobody can relate them. Nobody can see that you were paid both for mowing your neighbor's lawn and, selling marijuana, whatever, right? Whatever the things are that you do for fun. Nobody can relate those two. But as soon as you have some connection to a real name, it all starts to break down. So there is no anonymity as a core thing. There are ways to deal with it. For example, there is something called what's called a mixer, where essentially you have somebody who provides as a service sort of Bitcoin money laundering, right? You put in money and you get it back associated with different, you gain control to another address that has the same amount of money than what you put inside, but it makes it harder to trace. And there are other coins, other cryptocurrencies that have anonymity as a first-class concern, right? So, for example, Monero is one of them, or Dash, and I believe Zcash. But there are so many, I lose track of all the details. I'm pretty sure about Dash and Monero, but you would probably have to look up what the state of the art is in early 2019 to be sure. Yes. Yes. Well, yeah, it's definitely a risk. I know a startup that provides Bitcoin tracing tools to forensic units in police departments, right? So it's definitely something that you can try. Probably it's just an arms race between the criminals and or between the ones who don't want to, not necessarily criminals, between the ones wanting to hide their money and the ones who don't want them to hide anything. Right. Okay. Good. So we have a bunch of alternatives left, but I'm not going to show more slides except the summary slides. I do want to address a number of things that I haven't mentioned. So I've explicitly talked only about two public chains, right? And you are aware that there are private chains, and you've heard a lot about Hyperledger, and there are many other alternatives of that. So essentially the difference here is that a public chain has to deal with a different set of problems. Because a public chain always aims for complete openness. Anybody can participate. Now, depending on what your use case is, you might not need that. Right? If you say, all that I want to do is have my tight group of partners collaborate to do something, then you don't need this complete openness because you don't want somebody in Southeast Asia joining you or in whatever, in India. You don't want anybody to participate except the few people that you explicitly assign to the whole thing. Now, sometimes when people do that, they seem to miss that maybe they don't need a blockchain at all. Right, because very often a centralized solution or centrally operated solution is the much better alternative, much faster, easier, mature, well-known. So that is my number one beef with many private blockchain implementations. Many private blockchain implementations are just stupid and shouldn't be blockchain implementations. But there is a certain case where you have partners who don't trust each other fully and who have some dynamics in there where a private blockchain might be a good alternative. I explicitly spend so much time talking about the public ones because I'm not at all ready to dismiss them yet. I strongly believe that both Bitcoin and Ethereum have a future. I can imagine that one of them, or something very much like them, will survive in the long run. Because I'm reminded, because I'm an old person, of something like the Internet. When the Internet came out, my company back then was still doing VANs. Does anybody remember what a VAN is with a V, a value-added network? We were exchanging X400 mails. We maintained addresses in X500 format. And my boss at least was very sure that this crazy thing called TCP/IP and this ridiculous thing called the Internet could never be the basis of any serial finance. I don't know, sort of turned out slightly different. So I can imagine that while we dismiss Bitcoin and Ethereum right now and look for real solutions within a company with private blockchains, we may be wrong. This may not be the best solution. Because if you have something like Ethereum, which is programmable, maybe you should invest your time into programming on top of Ethereum and leave the operating of the mining nodes to a larger community that's already there instead of trying to set up your own. So that's one thought that you might consider. I do think that this stuff is very cool. So I don't make my money exclusively with this, right? I make some money, but it's negligible from the other stuff that we do. So I don't have anything to sell. I still think it's very cool. I still think it's absolutely worth it. So it's great that you're here and informing yourselves about this whole thing. Talked about this. I think I've said this as well. I think it's one very cool thing is that the barrier to entry is so low. It takes very little effort to start playing with this stuff, right? If it's one of the public blockchains, you don't need anyone's permission. You can just start doing it. This may go wrong, like with the DAO, which you may or may not know. It doesn't matter if you don't. But essentially, you can start playing with the stuff immediately. You don't have to ask for anyone's permission, and that's a very cool thing. So I think you should do that, and then follow the standard advice of disrupt or be disrupted. That's all I have. Thanks for listening. Any questions left? Yes, please. Puya. Yes. Mm-hmm. 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 Oh yeah, that's a very good question. There are two very good questions. One thing is you can continuously update contracts; they just become new contracts, right? You can't modify an existing contract because that's there. You just create a new one, and you hopefully have designed some way of redirecting people from the old one to the new one from the beginning. So you have to take the fact that stuff is immutable. You have to take that into account, but you can manage it. In fact, immutability is a good strategy even if you're using Docker images, right? If you're deploying a Docker container, then you don't change this Docker, you provide a new version of the Docker and then deploy that. It's the same thing. The other part is also very important. Most people should put most of their solution not on the blockchain, even if they're using a blockchain. It's a very typical pattern that we see emerging, that people build a very significant distributed system with lots of participants and lots of interaction and messaging and all of that with lots of cryptography, but only a very, very small part is actually maintained on the blockchain because the blockchain is very slow, and it's so slow because it gives you those trust guarantees. So if you can have a mixed strategy, like for example, registering people and checkpointing certain transactions on the blockchain and doing the bulk of the stuff outside, this gives you a very scalable architecture. It also gives you a chance to use one of the public blockchains for the small blockchain part that you do there, because you keep all the private data outside anyway on your own solution. So hopefully, if you build a typical solution on top of Ethereum, my guess would be that the relation of Ethereum Solidity code to other code is 1 to 100, something like that. But the most of the stuff will be outside of the blockchain. So maybe one last question and then we call it a day. Yes, please. Yes, there is a reward, and there's also a riddle to be solved. It's a lot more complicated algorithmically than the proof of work thing in Bitcoin, but it's still proof of work. But they try to move to a proof of service model. A proof of stake model. That's what Ethereum moves to, which very briefly works so that you stake an amount of your virtual money. You say, I'm willing to prove that I really believe this is the outcome of this consensus discussion, and I'm willing to risk whatever amount of Ether, I don't know, 1,000 Ether. I'm willing to risk that. If I'm lying, then the day will be gone. If I help solve consensus, then I will get a small percentage as an added benefit of staking that money. So essentially, depending on the stake or on the amount of currency you have within the system, you are allowed to take part in votes. There's some randomness mixed in. It's still a hybrid system with the proof of work and the proof of stake thing, but it's slowly moving to that other thing over the next few years. I think so, yes. I think so. Sorry? Not yet. Okay, thank you. Not yet. Thanks for the correction. Okay. So, it was great. Thanks, and have a good conference. I'll be around for a while.